I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, welcome to The Naked Scientist. This is the show where we bring you the latest breakthroughs in science and technology with me, Chris Smith, and with Phil Sansom.
This week, we're tackling a deadly serious subject, the science of custard. We're covering the chemistry of eggs, custard powder explosions, plus that most important question of them all, is custard better, hot or cold?
And in the news, a possible answer to why we get the hiccups, and how reliable or unreliable is your family tree.
The Naked Scientist podcast is powered by ukfast.co.uk.
Now, first up, solar power is a very important part of renewable energy production, but the current generation of photovoltaic cells, those are the big black slabs that you see on the roofs of houses, are extremely heavy chunks of silicon. And not only do they take a lot of energy to make and to install, they're going to be jolly difficult to recycle in a few years' time when they need replacing.
Which means that the discovery by Cambridge University scientists of a new solar panel material called a perovskite is welcome news. It works as well as silicon, but it's thin enough to spray onto a surface, making it very light and cheap to deploy. Sasha Feldman.
We discovered a new material that could actually revolutionize solar cell panels on your rooftop. It's so-called perovskites. And a perovskite is a new class of crystalline structure that is based on a mixture of organic and inorganic building blocks.
In terms of its ability to generate electricity, will the basic principle be the same?
It will to some extent. We will still absorb sunlight, and the energy that light carries will then generate a current that we can use to store electrical energy. But the way this one works is slightly different in that usually you would expect for something like silicon a very precisely engined atomic crystal structure where every atom sits exactly where it's supposed to be. That matters because if you absorb light and generate charges, you also want to extract those charges and get them out of this material. So you don't want them to be stuck at disordered sites. But here we now have actual disorder that we want to be there because it helps to localize these charges.
What's the material the perovskite you've invented made from?
So there's quite the mixture of different ions in there, but most pronounced are lead and iodide, and then also some bromide. And they self-assemble into a very disordered energy landscape. You can think of a mountain and valley kind of structure in this material, and the charges will just roll down to the minimum, which is the valley. And there they will just accumulate, and we get more and more out of them, and then we extract them very easily.
So when you say you get a landscape, you get peaks like the mountains, and then valleys are dips between them. So it self-assembles into that sort of architecture in energy terms. And when the sunlight hits it, the charges all roll down like rainwater going into the valley, and you get a puddle there. Rather like we would tap off a river, you can tap off the flow of charges that have collected there.
Exactly, that's exactly right. And the funny thing is we did not anticipate that this would happen. We actually wanted to make a very flat landscape and just found this to assemble in this way. But then we found out that, as you said, it's actually easier to extract from these filled charge puddles.
How do you, for want of a better phrase, get a pipe into the puddle then to draw off the charge? If it's so disorganised, how do you know where those puddles are going to be? And therefore, how do you get at the charge?
We actually don't. So far, we just randomly pattern substrates and then hope that some of these puddles actually are aligned with our electrodes at the bottom. But due to the fact that these are so incredibly thin, which is just 200 nanometers or so, or a thousandth of the diameter of a human hair, it's quite easy to just somewhere have an electrode sitting because these puddles are still quite small.
I suppose a massive advantage is, given it's so thin, compared with a massive slab of silicon we currently put on the roof, where you've got arrays of solar panels weighing a ton or so to generate a modest amount of electricity, this is going to be extremely light. So there must be enormous numbers of benefits of not having to transport heavy materials, not having to recycle enormously heavy materials, etc., that come from this.
Yes, so you can envision actually something like flexible electronics from this. Because we work on such thin films, we can just print them like an inkjet printer on top of plastic substrates, so to say. And you could even integrate them in something like a jacket, for example. And then your jacket that you wear actually powers your phone in the end. That would be the dream.
So you've become a human solar panel.
Yes, basically. And also it can be used as a display in the same way that we absorb light energy to get electrical energy out. We can now think of putting electrical energy in to get light out. So this seems to work as well.
In terms of its performance, though, because that's the key thing, isn't it, is how good is it and can it give silicon, the traditional technology, a run for its money? Is it any good?
So actually it's performing astonishingly well. Around 25% efficiency, and you have around the same number for silicon. So it's reaching that level of efficiency, which is really astonishing given how easy and cheap this will be to produce.
And in terms of its environmental footprint, your material's got lead in it. That's not very nice, is it? We're trying to reduce our lead usage if we can because it has toxic and other effects. What's the environmental footprint of this?
So that is correct. There is lead in this composition, and we need it as of now. But if you have a bit of a comparison to the dimensions of lead we need here, if you envision just coating a whole football field full of our solar cell material, because it's so thin, just 100 nanometers or so, the amount of lead you will need to do this job is still less than what's on the top of your nail, of your thumb, for example. So compared to something like a lead sulfide-based battery that every one of us has in their cars right now, that's really a very, very small amount of lead.
And it won't fall apart in 5 minutes.
So they do fall apart within a much shorter time than silicon does right now. But given that we only have been working on this for the last 8 years or so, the increasements we got in the lifetimes are astonishingly high.
God, that's so cool. I can't get over it. Spray-on solar panels. That's Cambridge University's Sasha Feldman. That work appeared this week in the journal Nature Photonics.
Now, this ought to be a very, unfortunately, familiar noise to many.
Yes, hiccups are uncomfortable and always seem to happen at the worst times. And there's not yet a clear explanation for why we get them. They're involuntary spasms of the diaphragm that don't seem to have any purpose. But new evidence shows that for babies, hiccups might actually be helping their brains develop, meaning the reason adults experience them might be as a relic from our infancy when they were genuinely useful.
UCL scientists have suggested this theory after looking at 13 babies who happened to be hiccuping while their brains were being scanned for other reasons. They found spikes in brain activity that they think help the babies to figure out which parts of their bodies are which. Phil got the full story from the lead author, Kim Whitehead.
So what we've found is that when infants have a hiccup, they have a large change in brain activity immediately after the hiccup.
Is that them sensing their own hiccup, basically?
The way that we would interpret it, yes, is that the information from the feel of the diaphragm muscle contracting and potentially the sound that the hiccup makes, the hic noise, is reaching the brain and being processed by the brain by these young babies. And because we have a little sensor on their belly as part of our setup, we were able to look at the brain activity in real time.
Did you have to wait a while for them to hiccup? Because, am I right that babies are quite big hiccupers, right?
Exactly. It all relies on the fact that babies are big hiccupers. So this was a retrospective analysis. We started to become interested in it, and I realized that some of the babies hiccuped by chance, spontaneously during recordings that were being acquired for other scientific questions. And because they hiccup so often, so they hiccup about 1% of the day, just by chance, we will capture some of these hiccups during our experimental protocol.
Got it. So you've got your babies with the sensor on their chest. But how do you measure what's going on in their brains?
So we use a technique called EEG, and it stands for electroencephalography. And basically, it's able to record the ongoing electrical activity in the brain. The EEG is completely painless. We can record it from the scalp with the little sensors. And the great thing about it is that it allows us to see brain activity change millisecond by millisecond. So that's the level of 1,000th of a second. So we see 3 separate brain waves that look quite distinct. And what we've seen from other aspects of our research is that when the brain processes sensory information, it wants to get multiple parts of information. So for example, it might want to process where in the body that came from. And then those later brain waves are still a source of a lot of research interest, but they're potentially about extra sensory information. So are other things happening at the same time as this sensory input that we're receiving? What other aspects can we classify in the brain?
And then what are the consequences of big spikes in brain activity when you're hiccuping for a baby?
So we know that brain activity is correlated with different outcome, for example, in the milestones at school. But that's really just a correlation. So with human data, it's difficult to prove what is causally related to brain development. But based on people who work with animal models of development in early life, they suggest that these really big brain waves that are very typical of the early life period help to strengthen sensory networks in the brain at a time when the brain is just starting to establish those networks that I was talking about, that we have a network for touch, a network for motor control, etc. And it's useful for the immature brain to have a huge brainwave where lots of brain cells get activated at the same time by a sensory stimulus, because it helps them to link up an experience that happens at the body surface or the muscles of the body, helps to link that with brain pathways. And we all need that as we grow up in order to be aware of our surroundings, be able to interpret sensory signals.
So the hiccups might be really good for the developing baby brain.
We think that they may have a role in the developing baby brain, exactly.
Isn't that amazing? Kim Whitehead there. And you can safely say that's one of the few studies where they did anticipate having a hiccup or two in their research. You can read the paper if you want to. It's in the journal Scientific Reports.
Still to come, a 3D display straight out of Star Wars, and our main event, the wild science of custard.
But first, we're always looking for ways to save the planet, and one potential thing that might help is building houses from more sustainable materials so we can cut the massive carbon footprint that's imposed by concrete. And that's no mean feat, because concrete actually accounts for more than 10% of our CO2 emissions around the globe. Now, one candidate material that's fast-growing and very strong is bamboo, and it turns out this week it has some very interesting thermal properties as well. And Darshil Shah, who's at Cambridge University's Centre for Natural Material Innovation, is here to tell us about them. First of all, why bamboo as a building material? What's exciting about it?
Bamboo is a fantastic material. It grows really fast, so there are over 1,000 species of bamboo. Some of these can grow at a rate of a meter a day or 1 millimeter every 90 seconds. And while it grows, it captures carbon as well as stores it within the material. And it is also abundant in certain parts of the world.
Is that bamboo that you've got in front of you? Because
yes,
that is massive. That's like a cannon.
Yes, and these can Of course you can.
This is huge. This is probably, 10 centimetres across, this bamboo tube?
It can grow substantially thicker as well, and the stems the cell wall may be about 15, 20 millimeters thick, and they can grow up to 20, 30 meters tall.
But you alluded to this just now when you were saying, this is a tube. That's not ideal as a building material, is it, like that, for all kinds of applications?
No, exactly. So engineers would like to convert it into some form of beam material or as panels, which can be used as walls, floors, and these are converted into those sorts of materials by cutting these columns into strips and then planing them into rectangular shapes, and then thereafter gluing and...
And is that what that is? Because you've got something that looks a bit like the size of a big house brick.
Exactly, and these can be substantially longer, 3 meters, and they can also be in board form as well.
So you've given me, as I say, something about the size of a big house brick, and looking at it end on, I can see that it's made of lots of little pieces of wood which have all been glued together. So you've cut they're about 1.5 centimetre by 0.5 centimetre wide chunks, and then they've all been presumably glued together. How strong is that?
So bamboo has the same stiffness as wood, but it is substantially stronger than wood.
When I introduced you, I said that you've discovered some interesting thermal properties about bamboo this week. So what was the motivation for doing that? Why were you even interested in that, and how did you do it?
Well, yeah, firstly, there has been a lot of research on the cell structure of bamboo and its relation to mechanical properties, and some of this we have done ourselves. But there has been little research into how the structure is related to thermal properties. The amount of heating or cooling that is required in a building is fundamentally related to the properties of the materials they are made from, particularly how much heat they conduct and how much heat they store, and also a better understanding of the thermal properties of of bamboo would provide insights into how to reduce the energy consumption of a building and the fire behavior of a building. If we are to make fire-safe buildings, we need to understand the thermal properties of these materials.
So how did you scrutinise your bit of bamboo?
What we did was we actually took shavings of the bamboo and then we looked under an atomic force microscope, and what it does is it heats the probe and you touch the surface of the bamboo, and as you move the probe across, the heat is conducted or not, and that gives you a visual image of variations in the thermal conductivity.
And what did you find?
We find that bamboo is with a structure with fibers produced in a manner in which there are thick and thin adjacent cell wall layers. The thick ones, which are oriented along the fiber axis, provide stiffness and strength in that direction, also conduct heat in that direction, whereas the thin cell wall layers do not conduct as much heat in that direction.
May I infer from that then that if I were to try to push heat through a piece of bamboo, it would go along the bamboo quite well, but through the bamboo quite poorly?
That is correct.
So how does that affect the way in which we either are going to make more materials like this big brick you've made with little pieces of bamboo, or whole buildings out of bamboo? How's this going to change the way we fundamentally use it?
Firstly, we realize because bamboo is a combustible material, we need to protect it in some form so that the properties in that direction do not soften so rapidly. And this is commonly done either through an intumescent paint or using some form of protective layer like a gypsum board, but also looking at graphene and how coatings from graphene might be able to divert heat from the bamboo.
They were talking about how we're going to live on Mars this week. And they were saying that they're going to grow bamboo on Mars. I think it's a great material to grow in the first human settlements on Mars. For all the reasons you said, it grows so quick.
Fantastic.
And you can do stuff with it, and it's a little bit of home from home. So maybe you should talk there's an opportunity for you.
That is very interesting, because I was watching Avatar a while back and I saw bamboo forests in that as well. And it's definitely something we need to look into more anyways.
I'm excited because it opens up the possibility for panda colonies on Mars.
Darshil, thanks very much for coming to tell us all about the research. That's Darshil Shah. He's from the University of Cambridge.
Now, moving from engineering to genealogy. If you think you know who your relatives are, you might want to think again. Because according to a new study, about 1 in every 100 of us doesn't have the dad that we think we do. This is called extra-pair paternity. It's where a man ends up bringing up another man's child. And city living, as well as lower socioeconomic status, make it more likely to happen.
Researchers at Leuven University in Belgium discovered this by tracking down 513 pairs of men who, according to parish records, shared a male ancestor up to 500 years ago in their family trees. Now, because men inherit their Y chromosomes exclusively from their fathers, if there'd been no naughtiness at all in their family trees, the genetic barcodes of the Y chromosomes of each of the pairs of men should match. But, in some cases, they didn't, with obvious implications. And by using additional genetic techniques, they were able to work out when in the family histories that assignation must have happened. Speaking with Amalia Thomas, Martin Lamuseau.
For the first time, we reconstructed the historical patterns of extra-pair paternity across the last centuries within a Western population. What is extra-pair paternity? When it's an event when a man was unexpectedly not the biological father of his legal child. What we found was that the extra-pair paternity rates were lower overall, around 1%, but depending on social context, we find that the highest extra-pair paternity rates were observed among urban families with low socioeconomic status, especially in the 19th century.
And how did you find out that these women had been cheating on their husbands?
But it's not only cheating, it can also be the result of sexual aggression. Extra-pair paternity has potential different causes. So what we did was persons who are living today with a common paternal ancestor in direct paternal line, if they have the same Y chromosomes. Y chromosomes are the chromosomes that each male gets from his father. In a paternal line, every man should have the same Y chromosomal variant. If that is not the case, then at least one extra pair paternity event happened across the generation.
So you studied the genes of over 500 pairs of donors who are alive today and compared that to the family records dating back up to 500 years. How can you be so sure that records that are so old are accurate?
We are quite sure about those genealogies based on civil records and parish records. And if we didn't find a biological connection between presumed related persons, then we know that there is at least one extra pair paternity in the past.
And what have you found out from this comparison?
Well, that the extra pair paternity rate is quite low in average. It's always around 1%. But what we saw now is that there were quite differences between socioeconomic classes, especially the low social classes in the 19th century. They had a tenfold higher extra pair paternity rate than farmers in rural areas. And this is quite surprising. We didn't expect this. We expected more in aristocratic families, especially because there is a lot of references to adultery in the 17th century in literature and theater plays. And so this looks like, based on our results, that it's not the case.
Could you guess, if you don't know exactly, why it's the socioeconomic status, population density, and particularly the 19th century where this happened the most?
Well, we don't have a real explanation because we cannot interview all these people anymore and say what is the reason. Is it because of adultery? Is it because of sexual aggression and rape? We cannot ask them again, but what we see is that in the 19th century, there was a lot of social conflict. Low social classes lived in very poor conditions. We also had a lot of cholera epidemics, especially in Belgium and in the Netherlands, where we looked. After the Industrial Revolution, it was not that good conditions, and there were much higher differences between the social classes. So it was, after all, not so surprising that we could see differences.
Sounds like the aristos of yesterday weren't always the randy bunch that they're made out to be. Martin Lamuseau, and that study was in Current Biology.
Now, here's a story from a long, long time ago in a galaxy far, far away. You can probably see where we're going with this, can't you? If you've ever wanted a 3D holographic style display like the one that Princess Leia uses in Star Wars, you might be in luck, because researchers in the UK and Japan have invented a device that uses sound waves to produce a 3D video, audio and interactive touch display.
And you know, one of the best parts, no flimsy red and green 3D glasses to wear. Nadim Gabani asked Peter Christopher from the Centre for Molecular Materials, Photonics and Electronics at Cambridge University to take him through how the new gadget works.
Help me, Obi-Wan Kenobi. You're my only hope. Most of us can remember hearing those famous words and watching, and marvelling, as R2-D2 projects in 3D Princess Leia's plea for help to Luke Skywalker and Ben Kenobi in the first Star Wars blockbuster. It was all very futuristic. But now, the future is here. Sort of. Scientists have created a new type of device that uses sound waves to produce 3D video, audio, and an interactive touch experience, all without the use of glasses or additional equipment. Peter Christopher researches similar technologies at the University of Cambridge.
For many, many years, people thought that wouldn't be possible. But in the last few years, we've begun to see people taking steps towards having 3D displays and full 3D displays, as opposed to the tricks that you use to make things appear 3D inside a 3D cinema or on a 3D television.
The display itself is about the same size and shape as a microwave, but with the door removed. And this is where the magic happens. The display actually uses sound waves to produce an image.
The technology these guys are using is very clever. They're taking effectively a speaker wall, very small speaker wall, and a second one matching it, and they're using that to form a standing wave. So I don't know if you've ever been to the beach where there isn't much of a current and you throw a log or a ball out to sea. You'll see that the waves will go up and down, but the ball will stay still. And with clever manipulation of the waves, you can actually move the ball around without actually moving the material.
The display works on the same principle, but moves the ball faster than the human eye is able to resolve, producing a persistent image. To add colour, the ball is illuminated with colour LEDs at distinct points during its travel, corresponding to the colour of the same point in the image it's trying to reproduce, just as if it were a pixel. This is a very interesting approach for making 3D images, but why are they using sound rather than light?
I hate to say this, as obviously they're my competition, but I think acoustic technology makes more sense in the short term. The wavelengths of light that people can use is much, much smaller, which requires you to control light on the scale of nanometers. Whereas if you use acoustic or sound-based technology, you only have to control it on millimeters.
And how small is a nanometer?
So a nanometer is 10 to the minus 9 of a meter, which translates to about 10 atoms.
But then how do they reproduce sound? The speakers in the display vibrate at a frequency of 40 kilohertz, or 40,000 times a second, well outside the range of human hearing.
The ultrasound waves that are used for controlling the ball are very high frequency, much higher frequency than you can hear. And the scientists are using a technique known as pulse width modulation to superimpose a much lower frequency sound wave on top. Not in an entirely dissimilar way to, say, your old FM radio would have as a kid.
Cleverly, the system is not just able to simultaneously reproduce images and audio, but also feedback through tactile touch. This works in a similar way to the image production, except instead of a ball being trapped and moved, it would be your finger. This new type of display could enable a whole new range of applications which require 3D interaction between the user and the content, such as entertainment, training, or gaming, for example.
I believe the technology is impactful primarily because the image is actually in space. So if you go to a 3D cinema, or you have a 3D television at your home, or you use an Oculus Rift or other heads-up display, if you use those technologies, they're using tricks to trick your eyes into thinking you're seeing a 3D object. This technology is cool because it's a step towards having the first truly 3D displays, as opposed to ones that only look 3D under a very specific set of circumstances. This technology is also very cheap in comparison to 3D cinemas, and you could do that for hundreds rather than hundreds of thousands of pounds.
So it sounds like what was once, a long time ago, in a galaxy far, far away, is now very much within reach.
Nadim Gabani reporting. You can also see the display in action on YouTube by searching the catchily named Multimodal Acoustic Trap Display.
And if you want to catch up on any of the other things that we've been discussing so far in the programme, the references and the transcripts are all on our website. That's nakedscientist.com. Time now to head over to our mailbox. This is the part of the show where we read out your correspondence.
James Miller has been in touch to say, I was fascinated by your description of using NMR and mass spectroscopy to identify chemicals. I am 72 now, and in 1969 I was working at ICI in Runcorn in a group doing the same thing. Using software and novel permutations and combinations, I was able to identify chemicals from traces by their signatures. I wonder if the techniques I developed have got lost in the sands of time. Keep up the good work.
Thank you very much, James. Meanwhile, listener Josh says, hello, he's a big fan of the podcast, and he has a question. Now, why is it that when you try to keep your hands still, they go shaky? Any thoughts, Phil?
Yeah, it's a good one, and it's definitely relevant to me. You'll definitely have noticed that I can't really keep my hands still. I'm always fiddling with them. Josh, for me, it's not when I try to keep them still, though. So for you, there could be a number of reasons. It could be what's called an intention tremor, when you're thinking about moving your hand at any moment and it just tremors. Alternatively, it could be adrenaline if you're getting nervous. Or maybe you've been drinking a lot of caffeine, or using an asthma inhaler a lot. Or if it's genuine hand tremors and it's getting worse, probably worth going to see a GP about. There could be something going on in your cerebellum.
And thank you, Mark, who got in touch. He says, not a fan of bamboo at all. Nothing to do with its carbon footprint. It's to do with suppressed memories of being caned back in school in the 1960s.
Oh, poor Mark.
Sorry to hear that, Mark.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for your audio and video productions.
You're listening to The Naked Scientists. It's me, Chris Smith, and Phil Sanson. Now, in this half of the show, it's all about custard. And as the weather in the Northern Hemisphere gets a lot colder, we are entering the season of hot drinks and stodgy puddings. But the big question is, when you have your pudding, what do you put on top?
Yes, it's custard, it's delicious, but you'd be surprised how much science there is behind this humble dessert. Stick around for the chemistry of custard, including walking on custard, custard powder explosions, and it turns out to be a provocative topic in the Naked Scientist's office.
I think custard is the only acceptable thing that you can add to desserts. No ice cream, no cream.
Only custard, no ice cream?
If there was an option, always go with custard.
I can't go with this purist philosophy. Custard is great, but ice cream is also great.
Let's be clear about this, right? There are other things that are tasty. Ice cream is great, but when it comes to dessert, custard is the only acceptable addition.
Do you prefer it hot or cold?
There we go.
Right, we've had this argument in the office so many times, and Adam is consistently wrong. You have custard hot.
Hot dessert, cold custard. That's the correct way around.
On a hot dessert, you have hot custard. I don't care if it's July.
The point is to have a cold thing with a hot dessert, right?
Exactly. Cold thing on a hot dessert.
That's why you have it.
I don't want balance, I just want custard.
See, we do discuss very important topics among the team.
Now, whether it's hot or cold, most of us get our custard by taking custard powder either from the packet or from the tin. But to a purist, neither of those are actually custard at all. The real stuff involves eggs, cream, and some very careful cooking.
And to find out more, I went over to Parker's Tavern in Cambridge to meet the head chef, Tristan Welch.
Custard is probably up there with my top 3 sauces of all time.
Why does it rank so high?
It's home memories, it's childhood memories actually. It's a very comforting, creamy sauce that reminds me, certainly, of great family occasions.
Why don't you show me a little bit about how to make it? Let's start off.
Yeah, absolutely. So let's start by making a really classical custard, or the French might call it crème anglaise. All we need really is egg yolks, milk and cream and sugar with an infusion of vanilla.
At a fundamental level, is this what custard really is?
This is the complete definition of custard. This is what every other custard has been based upon.
Eggs, milk, cream, sugar.
With a bit of vanilla. Custard is the building block, one of the foundations of the modern world's desserts and anything else to do with the kitchen. A quiche, for instance.
No.
Of course a quiche is a custard.
I don't believe you.
Yeah, a quiche, a flan, and ice cream's another custard, actually.
Ice cream's a custard?
Yeah, absolutely. Actually, what we're doing here is a classical custard base. But if you take this custard and you put it in an ice cream machine, you've got vanilla ice cream.
Is it still custard, though?
Of course.
I'm finding out that a lot of things are custard that I didn't realise were custard.
Yeah. Everything's custard. It all comes down to custard.
Let's make a start on this, because you've got your pan here on this induction stove, this mini, almost hot plate.
And that's basically ticking away with our milk, cream and vanilla and creating an infusion. Now, in this bowl here, I'm mixing sugar and egg yolks. And that's going to give our milk and cream consistency, because when the egg yolks cook, the proteins coagulate a bit. It creates a viscosity, so a thickness to the milk and cream, and that is really what we know as custard. So our milk and cream has been infusing with our vanilla for about 20 minutes, a gentle simmer. The aroma is just fantastic. It's like childhood memories coming back. It's like a sweet shop. Now I've got our eggs and our sugar. I'm gently going to pour on the milk and cream, and this is called tempering the eggs. And this is really important. If you pour the eggs into the milk and cream, it will scramble them. So you pour about half of the milk and cream onto the eggs, and I can put that into the pan safely without it splitting.
And what do you mean by splitting?
Basically, if you cook the eggs too far, it looks a little bit like scrambled eggs floating in water.
And if I understand right, custard is all about cooking it to the point before it splits and you get the scrambled egg horribleness.
Absolutely. The magic temperature here to get it to is about 82 degrees centigrade. Oh, look, you can see now.
It's already thicker.
Yeah, absolutely.
You just had a spoonful.
It's delicious. I can't help myself. Never trust a chef who doesn't eat his own food, right?
Yeah. Is it my turn?
Yeah, you can have a taste if you want. You want a taste? Sorry.
That's gorgeous.
Shall I show you how this goes wrong?
Yes.
Okay, let's overcook it. It goes completely against my DNA, by the way. So what I'll do, I'm going to take out half of it now, so I only ruin a part of it. I'm just taking it above a safe level to cook out for an egg, so I'm essentially going to boil it. And you can see the bubbles coming up there now.
Oh no. There's little solid bits forming in this beautiful, lovely custard.
There you go. Watery. It's like, essentially it's curds and whey. It's starting to look disgusting, starting to smell disgusting. God dear me, don't tell my mentors, they'll go crazy.
How do you feel?
I feel split.
So Tristan, how often do you make custard in your kitchen?
More than daily. Our pastry chef probably makes a custard about 12, 15 times a day.
That's a lot of custard.
It's a lot of custard. It's a lot of eggs.
Now, I know that if someone couldn't eat eggs for whatever reason, this would be a good custard alternative. What are you making now?
So this is custard powder. This was the first custard that I knew, and it's the first custard which a lot of people knew in the UK.
It's custard as I would make it.
Poor you. So this is a custard powder, and basically the recipe is vanilla extract, corn flour, and colouring. We actually use this in some of our recipes in the pastry kitchen instead of corn flour because it's so high in corn flour.
Now, how can it be custard if it doesn't have that crucial ingredient, the eggs?
It's like how you say a vegetarian burger is still a burger without the beef. Poetic license is allowed, I think.
How does it work then if it's mainly corn flour?
Because it's got the cornstarch in it, you have to mix it with the cold milk and you bring it gently up to the boil. So what I'm going to do here, I've got our custard powder, and you've got to add a little bit of sugar to it, and our milk, and I'll just mix those in. You have to keep it stirring, otherwise what may well happen is the cornstarch will fall to the bottom of the pan and then start to cook before the rest of it does, and that will get you lumps again. Oh, here we go. I can feel it now on the whisk. Now you feel it getting slightly thicker. If it was green, you'd think it was slime, right? And
It'd be witch's cauldron.
And there we are. That is our powdered custard.
The powdered custard has a lot more yellowy colour and thicker texture.
Yeah, I think the colours, you're right. It is a little bit lighter. That's really dependent on the type of egg yolks that you use as well. So if you buy the bright yellow egg yolks, that will change the colour. But the consistency is something else. I like egg custard, right? I mean, egg custard's it's a real occasion. It's expensive compared to bird's custard, it really is. But it's really delicious, you know. It's a bit like a Rolls Royce versus a Ford Cortina, you know. But you know, when you go egg custard, it's very difficult to go back.
You've done all the custard cooking. I guess I'm on washing up duty?
Yeah, now, please.
Thank you very much to Tristan Welch from Parker's Tavern. And luckily he didn't make me do any washing up in the end. And the custard really was amazing.
Yeah, where's mine?
I might have eaten it all immediately. Well, now that we know the how of making custard, it's time to look at the why. What's happening at the molecular level when custard gets cooked? With us is chemist and chef Liliana Fruk. Welcome.
Now, Liliana, we've heard from Tristan about egg and egg proteins. He says are critical to his original custard recipe. So let's look at that first. So what is the egg yolk doing to the mixture to make that happen?
So egg yolk is full of proteins and fats, and they are basically, if you would centrifuge, if you would divide egg yolk, you will see that there is a little bit more liquidy part and a little bit more granular part of the eggs. And this is composed of fats and proteins mixed together. So when you basically heat up your egg, when you are in the process of making the custard, you are basically unfolding the protein structures. Proteins usually have globular structures. They have three...
Like a ball of wool?
Yes, so they're like three-dimensional. And when you heat them up, you unwind them. So they become a little bit elongated, longer. And you do this because the heat is used as a catalyst to destroy a particular molecular bonding by which these proteins are held together.
Do we know what that is?
So this is disulfide linkage. This is the linkage between these two tiols. And these tiol molecules, they actually give sometimes very smelly
so hence
kind of
eggy
odor.
smells.
Exactly.
But they're like molecular Velcro that hold the balls of wool together. And if you break those bonds, the protein strings out into long chains. But why does that make the custard?
And then these long chains now have the ability to kind of interact with each other a little bit easier. So what happens, you're creating almost a gel-like structure. And the beauty here is that you do need to have some minerals. So you need to add a little bit of salt and you need to add sugar. Sugar forms a tiny little coating on top of these molecular structures, which are now unwound. So they don't kind of assemble very quickly. They don't form a very rigid structure and they don't turn hard.
So I was just going to say, rather than a series of balls all sitting next to each other, once you allow them to chain out into strings, you can imagine that they're going to basically link the molecule, this raft of proteins and other things like the sugar, all together. So you get this jelly forming, and that's what it's doing.
Exactly. And so this process needs to be slow, because if you heat up suddenly, and we heard
that was going to be my next question. Why does overheating and over-egging the heat, why does that make a difference?
Because you are then removing this layer of sugar that protects a really strong binding and strong kind of unregulated process. You are just destroying it. If you heat slowly, this process happens slowly. You are slowly interlocking all of these structures, and you are creating nice gel.
So that's how egg works. What about the more, for want of a better phrase, poor man's custard, the stuff that comes out of a packet that we learned from Tristan does not have eggs? It's based on starch molecules. How does that work then, Liliana?
Starch molecules are also involved in thickening, in formation of this similar gel as the egg is forming. It's just the process is a tiny bit different.
So what actually is starch?
Starch is the polymer made of glucose. That means these are many glucose sugars which are bound together in the long chains.
So that's why it's similar to what the egg does. When you unchain the egg by heating, breaking those sulfur linkages that you mentioned, you get long chains that are sticky.
Yes.
You do the same thing with the starch.
You do the similar thing. It's just the starch is made of a glucose that doesn't have any thiols. So the principle is a little bit different, because the structure of starch is different. So it doesn't contain any thiols. So there is nothing to be broken. Exactly. So instead, if you heat the starch in water, the granules are formed which are embedding lots of water, and they swell. And as you keep on heating, the viscosity of the whole solution will change, because now you have these huge granules which are formed. And at a certain temperature, they will burst. And as they burst, they release tiny pieces of molecules which then act to cross-link these long linear pieces. So basically what you are now creating is a gel, which is a combination of different molecules and molecular species made of glucose, which are previously have been part of the starch.
So it amounts to the same outcome. It just uses a different chemical route and different ingredients to get there. But the basic premise is that you end up with long chains of molecules that are cross-linked together, and that forms this jelly.
And that forms this beautiful texture that we all like.
Liliana, you've brought in some custard for us to try, but it's not a custard that I've seen before. What's the story behind this?
Yeah, I'm enjoying mine. It's nice.
You
can come again, Liliana.
It's delicious.
So this is the best-selling Croatian custard, and it is a poor man's custard because it doesn't have any eggs, but instead it uses starch and a little bit of sugar, and it can be done with water. It doesn't necessarily require milk, but it's much tastier if there is a full-fat milk that is used for making this. And actually, this was a kind of a tiny social revolution when this starch-based custard came and became available to the masses, because eggs are expensive, and they have been expensive, and so they were considered a luxury product, and anything that was made with eggs was a luxury product. So having a possibility to have a wonderful custard made without eggs gave the opportunity to everybody to enjoy a beautiful dessert.
Equal opportunity custard.
Equal opportunity custard early on.
I have to say,
I need to tell you that in Croatia we have this luxury version custard, which we all really adore, and it's made with a liqueur which is made of rose petals.
Oh, wow. Well, next time you come, you can bring that, because you're going to be opening a restaurant. Every time you come on this programme, we talk about your restaurant. You're going to open in Zagreb. Very beautiful city. Hello to my Australian friends at the Australian Embassy in Zagreb, Libby Petrovic, who's the Australian ambassador, who made me very welcome a couple of years ago. I'm looking forward to coming back and seeing them all, and I'll drop in and see your restaurant. You're going to serve this?
You should. Oh, we will definitely serve the rose petal version.
I'm excited. I want to go see it.
Liliana, thanks very much for coming in and explaining the chemistry of custard to us. That's Liliana Fruck from the University of Cambridge. We're midway through our custard science extravaganza, and we've heard about how to make custard and also about the chemistry that occurs while you're cooking it.
But now it's time to move from chemistry onto the field of fluid dynamics. And did you know that you can actually walk on custard? It's true. Well, specifically custard made from custard powder, and that's because the powder is mostly cornstarch. When you mix that with a bit of water, you create a liquid that acts like a solid when you try to move it too quickly.
The stuff is lovingly called oobleck in children's science demos, and it's a great example of a non-Newtonian fluid, specifically one that's shear thickening. That means it becomes a lot thicker and more viscous the more shear force, or push, you apply to it. And Phil had a go at making some for himself.
Oh, that doesn't look good. Oh no.
You do not want to work on this.
That's a liquid.
That's a very liquidy custard, yes. I don't think you even want to eat it.
That is me with fluid dynamicist Mazi Jalal. And the reason we're so disappointed is that while it's true you can walk on custard, you can't do it by following the recipe on the back of the tin. Here is Mazi explaining how it's supposed to work.
Most of the fluids that we're familiar with, like water or honey, are Newtonian. So basically what it means is that they have one constant viscosity, but many materials, like many foods, their response depends how fast and how hard you push them.
So if you hit it harder, it becomes more viscous? Is that right?
Again, depends on the material. So let's think about ketchup, for instance, which is a very common example of food for shear thinning materials. Ketchup, if you hold it, it doesn't come out. But if you put enough stress on it, it starts to flow. So you basically somehow yield it, and after that, it looks like a shear thinning materials, meaning the harder you basically stress them, the faster it flows.
That's why you hit the ketchup bottle to get the ketchup out.
That's exactly what you do.
That's shear thinning, where the liquid gets runnier the more force you apply. The other type of non-Newtonian fluid is like cornstarch and water. That's shear thickening, getting thicker when you apply a force to it. It happens when you have these tiny particles suspended in a liquid.
For instance, in cornstarch, there are basically starch particles that interact with each other, and that gives this very strange behavior. Basically, these suspensions are in water, and if you press them hard enough, the solid particle of starch start to somehow make some sort of friction onto each other.
Is that something that applies to other materials in other places?
It is applied to almost any industrial fluid that you can think of. Cosmetic industries to oil industry, most of the fluids that you're dealing with are not Newtonian.
The science of dealing with flowing materials like this is called rheology. And if you're a rheologist, like Mazi, you might want to design a material to have the perfect amount of shear thinning or shear thickening. Now this stuff can get kind of extreme. I went to find out more from Lucasian professor of mathematics, Mike Cates.
There's a guy called Norman Wagner actually, who did have a big contract with the US Defense Funding Agency. And they were wondering whether if you actually shot bullets at this fluid, it could stop a bullet. And the answer is not quite. What you have to do is you have to get some of the shear thickening fluid and you have to laminate it between layers of Kevlar. Then that combination does seem to be capable, certainly, of stopping a stab wound and possibly a bullet.
Yep, you heard that right. Bulletproof custard.
The thing about the dense custard powder suspension is that it is a fluid. We know how it thickens like that and it jams. Nonetheless, it can fracture and fly to pieces. But if you put it in that sandwich with the Kevlar layers on the outside, that holds it in. The combination can stop a projectile, maybe a bullet.
Is this actual cornstarch custard powder that we're talking about here?
Cornstarch has become actually quite a good benchmark model system. It has just the right interactions, particles which are very hard, quite smooth, and also have some sort of little repulsion between them. And cornstarch, when you put it in water, the particles become charged so that they automatically get this repulsion. Of course, there are much more sophisticated synthetic systems where you make specified particle size, perfectly spherical particles, and some of those are certainly better than cornstarch in any particular application, like a bulletproof vest. In particular, cornstarch in water, if you came back a couple of weeks' time, it would be pretty smelly. Bacteria love cornstarch. They're going to eat your clothes.
So maybe don't expect birds to become the #1 military contractor. Anyway, back to Mazi and I, where we've managed to perfect our formula.
So this one has almost 3/4 of the custard powder, and 1/4 water. So now what you see is a shear thickening fluid.
Is it working?
It is working actually very well.
Can I try? Oh yeah, wow. It's really hard to mix when you're trying, but then when you just glide it through the liquid, it goes easily. That is bizarre. Thanks to Mazi Jalal and Mike Cates for their help there. And we actually have an update about Norman Wagner's work on bulletproof custard. It turns out that he completed that research in the early 2000s and is now working on shear thickening fluids for spacesuits and, would you believe it, sports bras. Support when you need it, comfort when you don't. No word on whether the US military is actually using the technology, though.
Now, speaking of the military, not only is custard a chemical cornucopia and a great case study for fluid dynamics, custard powder sometimes demonstrates another physical phenomenon, and that is combustibility. Now, custard powder is indeed flammable, and we've come out into the car park for a very good reason to show you why. And Dave Ansell, science demoist extraordinaire, is here with me to help me out. So first of all, Dave, why is custard flammable?
Well, custard's a fuel like any other, like wood or oil. It's got carbon in it, hydrogen in it. You burn it, those will react with oxygen and give off energy. Normally this will happen really slowly, in the same way that if you've got a big lump of wood, it'll take ages to burn. Twigs will take minutes. If you chop it down to a piece of paper, it might burn in seconds. But the real thing about corn flour, which is in custard powder, is that the particles are microns across, maybe 10 microns across. So if you can get the oxygen to them, they'll burn very, very quickly.
And to put that into perspective, microns being tiny, those are the size of particles that come out of the exhaust pipes of cars. These are really tiny particles.
Very, very tiny. That's a millionth of a metre is a micron.
And does the same physics apply to pretty much anything that's a fuel source? Because you mentioned carbon, hydrogen, oxygen in the molecules, for example. So basically anything that can work as a fuel, this physics applies.
Yeah, so if you can break up any fuel into very, very small particles and mix it with air, it will burn very quickly. That's not just things with carbon and hydrogen in them, even things like titanium will do the same thing. So there was a titanium factory which blew up in 2014, 2015 in the States, where they got titanium dust, the spark ignited it, and the whole thing went off, bang.
And essentially, in some terms of a real-world application, a diesel engine or an engine that's making a spray of petrol vapour inside the cylinder, air-fuel mixtures work in the same way, isn't it?
Yeah, you're splitting up your fuel into very, very small particles. You mix it well, it'll burn, and the smaller the particles, the quicker it'll burn. Probably the extreme example of this is gas. If you mix gas with air really well, it will go off with a really, really violent bang.
And now you're going to show us how it works. You've lit a gas torch in front of us, which is keeping us warm on this very cold evening. You have a thing that looks like a gentleman's pipe from the 1800s, but with an exceptionally long piece of plastic tube on the end of it going into it. And you have loaded the bowl of the pipe with...
This is custard powder.
Okay, and what are you going to do?
So basically we want to suspend this in the air, so I'm going to blow air into this pipe. The pipe's set off centre, so it kind of spirals inside the bowl of the pipe, so it mixes with air very, very efficiently. And...
Should we count down? 3, 2, 1, Dave's going to blow it in the flame. I don't have many hair follicles left now, or eyebrows, but there was an enormous fireball. Basically that was about 3 feet across, and it went in a fraction of a second.
Yeah, burns very, very quickly, lots of heat released. If that was a whole building going up, then you'd have serious problems.
And it's the heat that's released from that then causes the air to expand, and that causes the explosive force.
Yeah, as with any explosion, heat causing gas to expand, that then hits things, blows apart buildings. I mean, whole buildings have been completely destroyed by this effect.
Dave, thank you very much for demonstrating it for us. Demonstrator extraordinaire, Dave Ansell.
Wow, and thank you to our other guests this week, Tristan Welch, Liliana Fruck, Mazi Jalal and Mike Cates. Meanwhile, online, people have been chipping into our hot versus cold custard debate that we discussed at the start of the back half. A surprising 10% of you said you don't like custard, fair enough. 30% said you like it cold, but congratulations, Katie, the vast majority of you are with her and like your custard hot. Now to finish question of the week, and this week Adam has taken a bite out of this question from Vinny.
I have read mosquitoes have a preference for blood type and prefer people with type O blood over those with type B. Is this true? And how do they know the difference between types?
Are you one of those people that mosquitoes are just drawn to? Or, like me, are you lucky enough that you get to be smug that mosquitoes will only come to you as a last resort? Could your blood have something to do with that? I reached out to Imo Hansen from New Mexico State University to find out.
There is one study from 2004 on the landing preference of Asian tiger mosquitoes, Aedes albopictus, on people with different blood types. Shirawi and co-workers found that this species of mosquitoes prefers to land on subjects that had blood group O compared with subjects of all other blood types.
Uh-oh then for people with O blood types. But how can a blood type impact what's happening?
Blood types are defined by specific carbohydrates or sugars that are on the surface of the red blood cells. When they applied these sugar antigens to the forearms of test subjects, they found that subjects treated with the antigen for blood type O attracted more mosquitoes than subjects treated with antigens for all other blood types.
These antigens are also the reason people with A-type blood can't take from people with B-type blood. The H antigen is found on all blood types, so if you only have that, you've got type O blood and can give to others, especially mosquitoes, apparently.
With this study, these scientists confirmed an earlier study from 1972 that was performed by Wood and co-workers, and they showed that blood type O is more attractive than blood type B, which is more attractive than blood type AB, which is more attractive than blood type A. A more recent study from 2019 from Prasadini and co-workers shows that yellow fever mosquitoes also prefer blood type O if they can choose between the 4 different blood types in an artificial feeding system. The big question, however, is how mosquitoes can distinguish between subjects with different blood types, since host blood is usually not directly exposed to the air. Mosquitoes find their hosts using their sense of smell, so there must be some difference in the olfactory cues that subjects with different blood types excrete, but those differences are still unknown.
And it's worth mentioning the blood type isn't the only factor. There's loads of chemicals in sweat. And as Flummoxed points out on the forum, being pregnant and even a few beers can change how mosquitoes respond to you. Thanks very much to Imo for flying in with that answer. Next time we're tackling this one from Jeff.
How is it that there are rising sea levels impacting some island nations, such as the Maldives or Kiribati, yet 1,000 kilometres in any direction, there is no discernible sea level change at all?
If you can answer Jeff's question, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on the forum, thenakedscientist.com/forum. And that mosquito question, interestingly, I get bitten a lot, and I'm type O blood, so maybe that's the reason.
Maybe it is indeed. That is it for this week. Thanks, Phil, for putting the programme together. And do be sure to tune in next time when we're taking a trip into our biological future as we investigate the prospect for making artificial organs. No, it isn't science fiction. Meanwhile, if you like The Naked Scientists and you'd like to help support what we do, we'd be very grateful if you could make a donation. You go to nakedscientist.com/donate. It's very safe, very secure, and you can put your comments about the programme there. Speaking of which, if you'd like to leave us a review on any of the podcasting platforms that you're using, we'd love that too. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.